Welcome back to the Dr. Stats-A-Lot channel series on probability theory. I'm Mark Ledbetter, and this is video A of B for part 1 of section 1 of chapter 5, titled Functions of One Random Variable. This is also called Transformations of One Random Variable. Well, I'm excited about this topic, so why don't we get started? We begin with an overview of the lecture. In this video, we discuss the goals for the entire section, provide general information on functions of one random variable, and finally demonstrate using two examples how to transform a finite discrete random variable provided in table format or probabilities that could easily be placed in table format. Before we continue, it's important to provide some references. The material in section 1 has been developed from the following text, along with lecture notes from N. Raul Gigante at ODU in Norfolk, Virginia. By the conclusion of the videos for this section, along with the completion of the corresponding worksheets and assigned problems, you will 1. Be proficient at determining the distribution of the random variable created by applying a function to a finite discrete random variable provided in table format or as individual probabilities. Likewise, you should be able to use the inverse substitution method to transform discrete random variables, either finite or countably infinite, that are given as a formula. 3. You should be able to plot the original and new distributions of the discrete random variables to understand the effect of the transformation. 4 and 5. You should be able to use the two techniques listed here for transforming continuous random variables. You should also understand the role of the theorem that states that the CDF of a continuous random variable itself follows a continuous uniform distribution from 0 to 1. And finally, you should be able to sketch, not plot, the original and transformed continuous random variables to understand the effect of the transformation. The following information applies to all random variables, both discrete and continuous. The key point here is that a function of a random variable is also a random variable. And this makes practical sense. If we roll a fair die, the outcome is a random quantity. We do not know the value until after we roll the die. If we relabel the sides of this die to different values and we roll the die, we still do not know the actual value that occurs until after we roll the die, so it's still a random quantity or random variable. If we apply a function g to the random variable x and create a new random variable y, then the probabilities associated with the values or outcomes of y depend on the original probabilities of x. For any subset B in the sample space S of the experiment, the probability that y is in B is the same as the probability that g of x is in B. We simply replace y with g of x, which are equal to each other. So the right-hand side shows that P of y is dependent on g, on x, and thus on the CDF of x. Note that for some, but not all, of the possible transformations, we will be able to find a closed form for y. And for some of the transformations, we'll even recognize them as other known distributions. So let's begin with discrete random variables. The key point here is that there are no theorems or shortcuts. We have to use simple logic and care to make the transformations. In many ways, discrete random variable transformations are easier than those for continuous random variables, and in other ways students may find them more challenging. Authors such as Casella, Berger, Lehman, and Romano, along with Professor N. Raul Gigante, have chosen to use examples to teach transformations on finite discrete random variables. From this, one can conclude that these simple examples provide the most effective way to learn this technique. So let's take a look at several different examples. In our first example, we use a discrete uniform distribution on -1, 0, 1, and 2. We will apply a linear function y equals 2x plus 5. We apply the linear operator y equals 2x plus 5 to the discrete uniform distribution of x. Note that the 2 will stretch the distribution by a factor of 2. Then afterwards, the positive 5 will shift the result of 2x to the right by 5 units. We start with the number line for x, and we map x to y using the function y equals 2x plus 5. The first calculation for x equals -1 is provided in detail. First, we substitute -1 for x. So 2 times -1 is -2. Plus 5 gives us 3, so -1 maps to 3. Similarly, 0 maps to 5, 1 maps to 7, and 2 maps to 9. Since this is a one-to-one function, we have the same number of values for y as we do for x. The space of y is 3, 5, 7, and 9, and the probability distribution for y is provided in the table. While we have completed the transformation of x to y, it is important to discover the effect of that transformation on x. This is easily seen by simply graphing the distributions of both x and y. X, as we mentioned, has a discrete uniform distribution on the values of -1, 0, 1, and 2. The distribution of y is still a uniform distribution. However, the transformation spread out that distribution by a factor of 2 and afterwards shifted it to the right by 5. Be careful. For example, the multiplier changed -1 to -2, and then afterwards it shifted it to the right by 5 up to 3. So we cannot just add 5 to each value. The difference between 3 and -1 is only 4. The difference between 7 and 1 is 6. And the difference between 2 and 9 is 7. So the order of operations is very important. Also, we are not graphing y versus x. Instead, we are graphing x versus p of x and y versus p of y. For example 2, we start with the same discrete uniform distribution for x. However, this time we apply a 2-to-1 function to x, namely y equals 2x squared. We start with the number line for x, we map x to y using y equals 2x squared, and we see that -1 maps to 2, 0 maps to 0, 1 maps to 2, and 2 maps to 8. Now, if the support of x also included -2, it would map to 8 as well. Of course, x equals -2 is not in the support of x, but it shows that this transformation is symmetric about x equals 0. The support of y is 0, 2, and 8. In this first table, we demonstrate the value of y to which each value of x is mapped. Caution! This is not an acceptable representation for a probability distribution. Personally, I would not award any points for this first table since it does not demonstrate a basic understanding of probability distributions. It is simply an intermediate step that helps us understand that in this case 2 values of x, namely x is -1 and 1, both map to y equals 2. So there are 2 ways to obtain a value of y equals 2 from x, and each value of x occurs with a probability of 1/4. So we add these probabilities to get the probability that y equals 2 occurs with a probability of 2/4 or 1/2. The second table contains the proper probability distribution for y. Your answer should look like this. Now notice that the total probability for y adds up to 1. This is an easy check to verify there are no errors. So if the probability does not add up to 1, it is not a probability distribution and there is an error. Now let's take a look at the effect of the transformation graphically. We started with the discrete uniform distribution for x. The distribution of y has a different shape. It is triangular. We also say that it is unimodal with a peak at 2. The effect of the transformation is provided. First, we note that it is a 2-to-1 function. Then we discuss each operation in the function. First, the transformation squared each value, which made them all non-negative and also skewed them away from 0. Then the multiplier of 2 further spread out or skewed the distribution to the right, again away from 0. You may wish to start completing the worksheet for part 1 right away. The worksheet is for videos A, which is this video, and video B, the next one. Also, remember that the only way to gain proficiency in a STEM, that's science, technology, engineering, or math field, is by practice. Just as you would not expect to win a race or a game without practicing, you cannot learn how to do math and statistics without working the problems. Please also make sure that you add any notes you need in order to recall how to complete these transformations to your information sheet for this course. Please stay safe and take care of yourself, because I really hope to see you here next time.